All right, so today we'll talk about visualization on the web with VTK.js, JavaScript. And so I'm going to start with really we talked about visualization in the earlier lectures as a general concept. And I'm going to just revisit that a little bit to relate VTK to that visualization process. So I'm going to use the mouse here for the recording's sake. So really, I think I probably talked about these steps in our first lecture, but they really map or align with different processes of VTK pretty well, right? So we start with our data, and then I have here 3 different ways. You can kind of lump the last 2 as a single way as well, right? So we have recorded data that we capture from somewhere, or get live streamed. Recorded is probably a bad word for that. Simulated data and or mathematically expressed data, which are really kind of one and the same, but mathematical expressions might be simpler, a lot simpler than simulation. And then what we have, so VTK calls these data sources, and so we've kind of used that nomenclature in our graph here, and then VTK calls this next step filtering, and some of this comes from, I'll show you in the next slide, a program called AVS, which was kind of the first generic visualization tool, plug and play visualization tool that we had available. And so filtering, they distinguish from, say, mapping, where we're taking like data into like data, right? So we're taking some data that's a 3D volume, and we're going to process it and produce a 3D volume, right, of floating points, and we'll take floating points. The floating points, I guess we could simple it down to integers, but basically it means the same shape, the same topology, same topography of data into the same type of data. And which also includes taking geometry and turning it into other geometry. So we could take some geometric form and warp it in some way and get some other geometric form. Mapping, on the other hand, is taking whatever data we have and turning it into geometry. So if we have a 3D volume, now we're going to have some sort of data that we can render on our computer graphics systems. And so we want to have some geometry, which includes how they're colored, how they're shaded. And then after we have that, we turn our geometry into pixels. So this is again with our graphics cards. So here we have polygons and things like that. Down here now we have pixels, and then we have a display, which just means put this off on the screen, which is presumably attached to some hardware device. And so a lot of this comes from, like I said, this program called AVS. So this notion of scientific visualization being a flow of data from one step to the next, to a large degree comes from this product called AVS, which stood for Advanced Visualization System. And they had this visual programming language that mapped out, that showed you what was happening. So we had read data here. The blue lines were like scientific data, so volumes. The yellow lines, so they even represented, so it's kind of visualization of the visualization. Color systems were encoded in yellow. And so you knew you could only connect a yellow to a yellow, right? If you generate a color map, which we talked about a few weeks ago, the slicer indicates that it needs a color map. It needs some sort of mapping of colors. And so it has this little yellow tab. So over here in isosurface, the yellow tab is unconnected. And so it just looks like a little rectangle. And then when you connect it, you get this little pyramid on here. And so there we can see how the visualization is working. And you can see some of these things like isosurface can either take 3D data or it can take 2D geometries. And then the output of all 3 of these, the volume, boundaries, the slice through the data, and the isosurface are red, which means it's a geometry. And then we render geometry, turn it into pixels. The pixels are this cyan here, and then more data. So we can take our pixel data, which is back to being kind of number data, and we can store that in a file. So anyway, I don't have a picture of the actual data, but this shows us what's happening. And VTK pretty much follows the same thing. It just doesn't give us the visualization, right? And we saw in Perview. Perview has a similar sort of visualization, but it simplifies it into a tree map. This one shows you that there's all sorts of ways that things can be connected in multiple directions. It's not necessarily a tree. It can be more of a graph data network. And so in VTK, we actually have to say by commands connect the output of our data reader to the input of our slicer or to the input of our isosurfacer. And so you'll see that in the code that we'll see in the next few slides. And so I just want to use that to kind of give you that. This tool, of course, is I think long gone, but it was copied by a few others, some of which are still around. All right, so that's what VTK kind of bases its architecture on. And so I've talked about VTK before, so I won't labor on this too much. But as with ParaView, it came from a group from General Electric. Actually, when ParaView came out, they had already split off from General Electric. So they split off from General Electric to create a company to maintain VTK. And especially at the beginning, it had multiple language choices. Python was added later on, but mostly it supports C++, Tickle, which very few people use anymore, Python and Java, and then of course for our web version, JavaScript. And it has no GUI, so that's kind of the big difference between it and the AVS thing I showed. It has, all the GUI is basically what you create as the programmer, and so you don't have the GUI to modify the visualization, you have the GUI to, or the steps of the visualization. You only have the interface to show what you're allowing the end user to manipulate. Right, so here's some reasons why you might want to use one language over another. C++ is mostly if you're going for speed, although since a lot of the code is already pre-compiled to C++, if all you're doing is making those connections, using Tickle or Python to do that really doesn't hamper the speed too much. It's only when you start doing mathematical operations in your program rather than just using the pre-built stuff it's all coded in C++. And then Java was introduced. I think the Java interface is maybe less, or certainly less popular than the C++ one, but it tends to be a little bit more portable. All right, so the first thing we're going to do, something very simple, is load up a sphere. And so all we're going to do is our data then is the sphere, right? And so VTK has everything for VTK starts with VTK. So we have VTK sphere source. So this is our data source. And then, as I said, we have to take our data and map it into geometry. So that's what VTK poly data mapper does. So in this case, it's a specific data mapper that takes polygons. That's the poly part. So sphere generates polygons. We need to map that into a geometry that our renderer can handle. And VTK, and I have these two colors here. VTK makes kind of a break here between the geometry and the rendering of the geometry. And so an actor basically has some properties that get applied to the geometry, like how it's lit, maybe what colors they are. And so the actor then is actually the part that's rendered, and the connection between these is slightly different in the code as well. And we'll see the sample code in a moment. And then we have our renderer, which produces pixels, which gets sent to the render window. And then they've added this last one where we have an interactor. So if you have mouse events or keyboard events, that's kind of looped in here, and we can make some manipulations there. So here's the old Tickle code for that. Basically, there's a class called VTK sphere source. We generate a new sphere, so this is kind of backwards from how we generally write things today. Sphere is the newly generated object, and then we use sphere and we have these methods, so we can set how many times around the latitude and how many times around longitude that sphere will be when it's turned into polygons. Then we connect it, so we have this VTK poly mapper, which is called sphere mapper, so this is the name of our instance of the class. And we set sphere mapper's input to the output of sphere. So we're just doing this line, this arrow right here. And then we have to have the actor. And so actor, as I said, is done slightly differently. There's only one mapper for an actor. So you always have set mapper to somebody's sphere mapper. So sphere, oops, did not mean to advance. So sphere mapper is actually the name of this instance. And so we just send that whole instance to be the mapper of this particular actor. So this is just kind of, we have to interface with what's going on under the scenes through these actor things. And so here we've just done this little arrow. And then on the next page, we do the rest of it. We create a renderer. We can set a background color. We create a window to render in. We create a size for that window. We create the interactor. And then the important thing, let's see, oh yeah, this bottom line here. so good thing that everybody's in the front couple rows, is we take the renderer that we created, which I called render one, because you can actually have multiple renderers. So in this case, render one, we add to it an actor that's the sphere actor. So that's really this arrow over here in the middle. We connect this actor to the renderer, and we'll see in a minute, you can have multiple actors feeding the same renderer. So you can have lots of geometry created through different processes that all get rendered together in the same scene. So that's the Tickle version. Here's the VTK.js version of that same example, and we can, I'll run this in a minute. But anyway, so here it's more of the variables on the left hand, where most languages put it, and we have the class here. So this class, oops, tried to click on my scene there. Here we go. Yeah. So we have a class, which is this VTK sphere source, misspelled a little bit there. And it is under a couple of different layers of VTK's system. And so we'll talk a little bit about that in a little bit. Anyway, sphere source is a source, and it's under the rubric of all the filters. And so we're going to create that. And then anytime we create a new instance of a class, we have this new instance thing, which I've highlighted in red for this particular page. And then we're going to store it in a variable called sphere. And then if we want to set the phi resolution and the theta resolution, we can do that with sphere dot that method name. You can actually give parameters into the new instance, but I want to map this closer to the Tickle example. I also turned on the edges of the polygons, and so when I run it live, you'll see that versus the picture I just showed. And then this part here is the rest of it. So we're doing everything on one screen versus two screens before. So we create a VTK mapper. Oh, actually, I take that back. Create the mapper, which is a rendering core. We set the connection. So just like we created this arrow, we're basically creating this arrow again. And then these three lines create this arrow. And I'm duplicating the sphere actor property. So this is redundant. I think you probably can do it either way. So here I'm actually setting in the polygons. Here I'm setting it on the mapping. Either way, it's only one of those is necessary. All right, and here's the rendering code. It's a little bit simpler. So I create a render window instance. I do a full screen rendering, which obviously there's a not full screen option, but we're just going to get full screen, so it'll take up our whole web page. We reset the camera to some view based on where objects are in the scene. We set this arrow here, connect the actor to the renderer. Then we get a render window, and then we tell that window to render. And if you don't do this, you won't see anything. And this is actually, I think, a loop, so it just actually continues to render. All right, so let's actually bring that up, even though it's pretty trivial. I want to bring it up in a web page just to demonstrate. So I'm going to escape from our PowerPoint and find my mouse. All right, this is the next example, actually. So I'm going to change that. You can see I'm reading this straight from a file on my computer, so this is not on the web. So here's that example. And so this is actually with 20 phi and 20 theta. And you can see I turned on the rendering of the lines, and so you can see that everything's turned into triangles, not just polygons, so that the sphere is made up of a bunch of triangles. All right, and so again, this is our interface. It comes with default things. I can zoom in and out. I can translate. And that's all built into the default renderer. You can also have other interface things, which we'll see, but I'm not going to cover how to code that in JavaScript today. Perhaps we'll save that for next semester. So there's that example. So let's go back, and we're going to enhance that just a little bit, just to demonstrate the notion of putting multiple actors into one renderer. And so here's the diagram for that. So here's our path we already had. And this one I'm calling, we have two sphere sources. One we're calling the data as a placeholder for actual data. And so this path still is there. So we're rendering that same sphere here. This one's lower resolution than we had. And then on top of that, for every point on the sphere, we're going to render a glyph, something that represents other data. And here we're just representing where the points are, but we could color it based on temperature or pressure or something like that. And so here, because those glyphs are spheres, we have another sphere source just to say that these are spheres. We could make this sphere source something else. We could make them cubes. We could make them arrows or cones. And we'll see some examples where we do that. And then there's a special, instead of this poly data mapper, we now have this glyph mapper, which takes two inputs. It takes the actual data, so we know where all the points are, and then it takes the glyph that's going to represent that data. And then there's lots of choices in here, such as how do I want to color the glyphs based on a particular data value, or if there's something that has a direction like an arrow or a cone, I can say how to rotate that arrow or cone based on vector data. Then it has its own actor, and then both actors feed into our renderer. And so I think I have some of that. I have highlighted here the new code is in darker font. So we have a glyph, which is another sphere source. It's just a new instance of it. I set its radius to 1/10 of the default. I could also have done that as an argument to new instance. Then I have to create a new mapper, which is a different kind of mapper. It's the glyph 3D mapper instead of the poly mapper. And now it takes two inputs, so I have to set two connections. So the connection number 0, which is just on this side of the line, which is, I obviously didn't pay sufficiently close enough attention to that, but the 0 over here is the one that's actually our data. And then the next one is our glyph. And so we set our sphere, which is represents our data in this case, to input port 0, and the glyph to input port 1. The output of the glyph goes to input port 1. And then down at the bottom, we create a new actor. So a new instance of the actor. And we set that to the glyph mapper, which is this geometry here. And then we add that to our renderer. So then we have a second arrow that goes to our renderer. And I won't show the source code for the renderings half since it's the same, but we will go back to the web page, and I'll change my sphere 1 example to be 2. And there's our new code. And if I remember how to bring up source. Do you know the key code to do source code on Chrome? All right, well, let's try right clicking. Oh yeah. There it is. I tried to do, all right, I had the wrong thing for you. So there's the source code for that one we were just looking at. You see, I was experimenting with some stuff, so there's a bunch of stuff commented out. So it's actually a lot less code than it appears here. It's more along the lines of what I showed on the slide. But at the top, just to look at it here, we're just kind of do standard HTML. We open up our body. I load in here the VTK.js suite. Here, this one I can move. Right. So there's a VTK.js collection of classes. Here I'm loading it from this company or this website called unpackage.com. And so they've brought it all for me. This way I don't have to install it on any of my own systems. If you're going to be serving your stuff yourself, of course, you'd want to install it on your own system so you don't rely on them changing things while you're not looking. But for development and testing things, this is a pretty good way because you can include everything just in this one line of script code. And then the rest of it's all just JavaScript inside the source script tag until we get to the end. Oh, can you? Okay. Well, that's very good. I should probably do that. Yeah, so the code here that's not commented is really not that much, right? So it's down here's the rendering bit that we looked at. Reset camera, and also setting the glyph mapper, the new glyph mapper. And then up here's the rest of it. So I'm creating several instances, a couple of which I'm not using because I was doing some experimenting. But anyway, there's the, so view-source colon, that's how you get it on Chrome. Anyway, so there's the code that generates this. So really, not too complicated. Once you get to the user interface, things get a little more complicated, which again, we can address in a later lecture. All right, so I want to switch back, talk a little bit about enabling WebGL, and then we're going to pretty much look at some kitware examples. I cannot get my mouse somewhere. There it is. All right, so our next page, oops, wrong way. There we go. So if you want to run VTK.js, it's based on, it's built on WebGL, I should say. And a lot of browsers, even today, don't come with WebGL activated. I think maybe partially for security reasons, partially because WebGL wasn't trusted, but it's become a lot more stable. So here's the tools to enable it in various web browsers. So in Chrome, you go to your settings by going Chrome:/flags, and then you'll find this at the, somewhere in there it'll say WebGL draft extensions. On mine, it's at the top, perhaps because I already enabled it. If you go to Firefox, it's got about config, which you can change configurations. You have to tell it that you'll be careful because you could void your warranty of Firefox. And then down here, you can see it's kind of backwards. So the flag is WebGL disabled. And so you have to set that to be false if you want to run WebGL, right? So it's kind of counterintuitive there. And then Safari, you can actually go into developer mode, preferences advanced, and enable WebGL. However, when I was testing this as I preparing my slides, I found no enable or disable WebGL. It just worked. So perhaps Safari has decided that WebGL is just part of the system. So I want to just briefly show those things. So running Chrome now, and then if I'll just bring up a new tab. Yeah. And so it has this experiment, so experimental features. In my list, WebGL draft extensions is at the top. And so you have enabled or disabled. And then there's a lot of others. There's some VR stuff in here and other things. So that's how you do it in Chrome. In Firefox, which I disabled it just for our presentation here. Of course, it pops up over here. I don't know how these screens are mapping. There we go. All right, so Firefox, I disabled it earlier today. And so you can see if I go to that web page, I get nothing. So if I now go to About Config, I can see I've already actually have that line highlighted. I can right-click on that and toggle it to be false again. And now if I reload this page, I get my sphere. So on the same computer, it's just loading the same page. And then Safari, I couldn't even turn it off, so I won't bring that one up. What's that? Yes. Okay, let's do it. Aha.
So on the bottom row, those are all the current versions.
So okay.
Everybody supports it except Opera Mini. And IE and Edge, they have that little one.
Yes.
That means that it's hidden behind that big flag.
Okay. So everyone else has pretty much just turned it on by default.
So everyone else has it turned on by default. It looks like Firefox has.
Yeah, I had to turn it off on Firefox just to test things. So, all right. 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 All right, so at least I learned something from our presentation today. All right, let's go back to the slides then. So for a lot of the rest of the slides, I'm going to kind of go through some of the stuff and just kind of give my own commentary on it. Some of the kitware work. So they have a pretty good documentation on their site. These are the main tabs: docs, API examples, and sample data. So the docs, really, it's kind of an odd thing. It's about 7 or 8 pages. The top one, first page is really super high level overview. It gives a quick code example very similar to the sphere one I showed you. And then it's like, here's how you can add new classes to VTK, and here's how you can add test things to VTK. So it jumps way down into the depths pretty quickly. The API one is kind of a good one if you're going to be working and developing your own tool with VTK.js. So it lists all the classes that have been ported thus far. So not all the classes that exist in VTK exist in VTK.js, which was a problem for me while I was preparing, because all my old VTK examples use stuff that's not in VTK.js. So I had to kind of work around things. And in the future, I'll have to figure things out for more advanced classes. Anyway, so not everything exists. If you have somebody who's written some VTK code, they may have more work ahead of them than just changing particular Python into JavaScript. And then I'll show you the web page for that, because I mentioned earlier that in order to just do, say, the source code, you had to go through filters, sources, sphere source, right? So to figure out what that list of things is, you really kind of have to go to this API page to demonstrate that. And we'll do that in a minute. Examples has a whole bunch of different examples of what you can do, some of which are basically tools that you can kind of jump right into and even download or upload your own data to and view without coding anything. And some examples show how to do the user interface stuff, which we're not covering today. And then they have some sample data that you can download. If you go to the sample data, just kind of a side note, oddly, these 3 tabs go away: docs, API, and examples. But there's replaced by a library tab, which takes you back where you can get to those tabs again. I don't know why they would design a web page that way, but that's how it is. So let's go, before we go into some examples, let's go back to the web. And here we go. So here's the top level page. You can see it has docs, API, examples. So the docs first page is this high level overview. It's got some nice pictures of what's possible. But let's go to the API one. So the API one, they talk about their book. And then they have these things that have all the classes that have been thus far ported into VTK.js. And you see there's common core, common / data model, common / transform has one, common system. And then there's filters, which there's one core filter, and then a lot of general filters, a lot of source filters. And so back to that sphere code, which I think is not, oh yeah. So in these lines here, this rendering core VTK actor, the way you know that's rendering in core before VTK actor is because you go and find VTK actor in this list, and you'll find it under rendering core. So there it is, actor. And then it talks about what arguments and stuff are there when you instance it, or if you want to use the get set tools for that. All right, so that talks about all the methods that are available under actor. But anyway, when you're creating a new instance, back to the top, this is how you know how to parse out the specific sourcing of the class. All right, after this, so we're going to look at some examples. And I have a bunch of slides to kind of give some commentary on some of the examples. So I'm going to switch back to the slides real quick, and we'll jump back and forth. All right, so the first one is the fact that you can actually take ParaView scenes, run them through a Python script, which they call a macro, and it'll turn it into a file that you can then upload into a scene explorer and view it. So here's 3 examples that are on the web. There's also, which I'm not showing, a filter called input stream, which actually lets you stream data directly from ParaView if you run a little web streamer on your system. So that's more advanced topic, which we can maybe cover next semester. But kind of easy thing to do is take this Python script, which they provide, load it into ParaView, and then that'll output into a format that you can upload to Scene Viewer. And I'm going to do 2 at a time here, and then we'll jump to the web. So another example, which is kind of already existing code, something you can actually upload your own data to. They provide one sample data set that you can play around with, but it's an application you can actually just, like I said, upload your data to and test it out. Here's the URL for it. One of the interesting things here, and we'll see this in a little bit later, is their color map editor has this little widget in it, which is very reminiscent of the one in Tort. And I think probably because Patrick O'Leary had his hand in, I'm gonna guess, I haven't asked him to confirm it, but I suspect he had his hand in the design of this widget to make it a really nice tool for manipulating color maps without having to go point by point. This widget's available to you when you get into the interaction stuff. We'll see that in a little bit. And so yeah, so let's go back to the web and just play around with those real briefly. So I'll just go read the examples page. Yeah, so they have the examples listed twice. They're in this 3 columns here in the middle, and then the rightmost column, they're duplicated. I think, well, some of them are duplicated. So the first one I was going to show, so we're not going to do the pair, we can do the pair v one, I think. Is that even in there? So I don't see the pair v1 over there, but it's going to be in our sample applications. Oh. I don't see it in the sample applications either. So where did I see that before? Oh yes, it is the Scene Explorer. There's a glare on the screen there. I can't read that one image. So which one is Scene Explorer, right? This one? All right. Yeah, so you can drag from your desktop and drop a scene file here. Down, if I scroll down here, here's the macro, the Python script that you can load into PairView that will output a file that you can upload. Where's the back arrow? Huh? Oh, it's a new tab. Okay, gotcha. Anything that's in this general area I cannot see. All right. So they have a few different data sets. I showed pictures of some of them. It's a special file format that they've created. But anyway, so this is a pair view scene. It's not a very colorful pair view scene, but anyway, pair view scene that you can that they've uploaded as an example file. So not a lot of controls. So you don't have any controls like we will in some of our later examples. And I don't know if that's doable in this scene viewer. So that's kind of the downside. Big one. Big simple one. Anyway, so there's a couple of pair view scenes. And then the other one that we talked about was volume rendering. Again, if you have VTK data, you can just drag it and drop it on there. But they've provided one example, in this case, with 3 different compression levels, I guess. I get that, there we go. So we'll load that data as kind of a familiar data set, right? I don't think this is the one I usually use, but another human male data set. And again, once I move on to this widget here, I can manipulate the shape of the color map and I can scale it back. In this case, I can't add new ones, so I can only have this one Gaussian. I can affect the transparency. It started with our rainbow color map, our not so favorite rainbow color map, but it's got options for different color maps here that you can choose between as well. So this is, again, so the code for all this is on that same web page when we go back. And so you can do self-shadowing or not self-shadowing with this. You can see it gets a little noisier in this particular example when you do it. Yeah, so anyway, so we have that widget and we have volume visualization that we can just do in our web browser, right? And let's go back to the commentary here. All right, so we can load geometries. In this case, it's a sphere with a texture map. So these are specifically OBJ files, or no, these are not OBJ files. These are in VTK format. So VTK files with geometries, and here you can choose whether you're in point mode. This is the points. This is the solid polygons with the sphere texture mapped on it. Not super interesting example, but again, if you have other geometries that are interesting, you can load those down. The next slide has OBJ geometry viewer, and OBJ is a format from long ago from a company called Wavefront. And so again, you have polygons with colors and texture maps on them, and you could just drop that. You zip the texture maps, what's called the material file, and the OBJ into a file together, and drop that in here, and you can view it, or just the random OBJ, which will be show up just as white. So let's go on to the next example. We'll do a few slides at a time. All right, so here's render a cone. So this is pretty much just like the sphere example I showed, except I wanted to add glyphs to my sphere, so I went with the sphere instead of the cone example. And it has, it has a more interesting interactor than what the default was. So they create this special window interactor instance. They interface it to the WebGL, the OpenGL. Oops, wrong way. And then they set up the interactor with the trackball feature style of moving around down in this bottom line. So that's the reason I put this particular example slide up here. So let's just quickly look at those. I have to move this over here. All right, so geometry viewer, again, you can test things out. They have some example things that you can look at. So here's like a clarinet piece or something, but it's probably some data set which they've sliced through. The OBJ viewer has those models that I showed and a couple more. So here's the Ferrari. So just standard OBJ file, just upload it, and pretty good interactive speeds on the web browser. And then the cone one. So there's two of them here. There's cone and simple cone. This cone here shows you some stats and stuff, whereas simple cone is very simple, but has the code that changed the interaction style with the trackball. Although I think that's probably the default. So I don't know, we gained too much. You can see that one of the things it did was change the window size. So now we have the scroll bar over here for our windows, whereas before they were all just coming up as a default size. So that's pretty simple. Let's go back to the slides. We'll try and progress through some more interesting examples. Right, so there's a whole list of filter sources, which I'm highlighting mainly because the thing that makes it interesting for me is that it shows you most of the top options that you have with that source, right? So we have a sphere source. I showed you that you can change the theta resolution and the phi resolution, but you can actually do things like change the radius. Well, we showed that too. But there's also this, in addition to the theta resolution, there's start and end theta, which means you can get part of the sphere. You can start wrapping around and stop in the middle and not go a whole 360, and in the phi not go a whole 0 to 180. And then you can turn the edge visibility on and off. So these are kind of the major options that your sphere source gets. There's also this point option, which has points randomly dispersed within a sphere volume. And so you can see that gives you a number of points and the radius of the sphere volume, not the radius of the points. And if you click on any of these other ones, you'll get similar things. I'm not going to even load up these two. The next one's where we start to get into some features of VTK that are more visualization oriented. So one of the things we can do is we have some data and we can warp the geometry of the data based on some value, right? And so the name of that filter in VTK parlance is warp scalar. And so there's a warp scalar class that you can load up. Here's kind of the relevant code out of their example. So we can create a new instance of a warp scalar. This one doesn't, they've pre-set it up so you don't have to do what leads up to the VTK warp scalar. But if you use that package.com, you have to do all the other stuff there. Here's where they're using the arguments to the instance to set some variables right away, some parameters right away. And then when it goes to, here's the user interface part, which I'm not generally talking about, but just to see that you can set some of the values with the user interface, and then every time you do that, you go ahead and re-render the scene. So I'm going to go ahead and let's play with that just a little bit, just to see what the warp scaler does. As soon as I find my mouse again, there we go. And I don't know if it's on our list over here. I'm going to move this here so I can read it. No. All right, so I'll have to go back to the examples tab. All right, so here, this will be under data processing, warp scaler. All right. Oops. All right, so here's our window. Comes up with some default parameters. We can, of course, adjust the radius of our sphere. If we get too close to it, it clips it off. So that's what the hole in the center was. We can set the resolution, which is going to, of the theta, which is the going around the sphere, and then the phi, which is going up and down. And so we're banding this thing basically every other one. So you get the lower the resolution, the less bands there are in the data. And then we can warp it. So we can take our data and warp it so the blue is warped out and the red is warped in. Or if I go this way, the red is warped out and the blue in. So our values are basically going, say, from 0 to, or -1 to 1. And so we can warp it in either direction by a certain amount. We can also warp it based, we can bring in the normal value of our sphere and warp it in that direction to get kind of a different effect. So if you're trying to produce some sort, we'll see actually a better example of the warping in the calculator in a little bit later, but that's kind of one of the standard VTK data tools. If you have a data set and you want to make a terrain style data or show flow through something, you want to show where the flow is faster by warping some plane, you can do that. And so that's the warp filter. Ah, darn it. Oop, wrong way. All right. So there's also this volume contour tool, which is data we've already seen, except in this case, it's not volume rendering. It's actually making a surface out of the volume. So I'll come back to that a little bit. Another interesting one is this zip HTTP reader. So I probably should put this one first or after the ParaView ones. And this one lets you actually have data that's available on a URL. And they can load that data by providing that URL to this reader instance of this HTTP data set reader class. And so there's no zip in this name here. So that's just to point that out. So here, some crazy URL, right? And so there's the data set stored there, and then we just read that, and we can read our data from a URL, and we can have that changing too, right? If you have several different files where you have some sort of progression in the URL name, you could load those and go over time. But so you can have a data reader that reads data via the web. All right, and then there's just like there were a whole bunch of sources, there's a whole bunch of interaction widgets. So again, I'm not going to go over the code for this because it's a little beyond what I wanted to cover today. But just to get a sense, so there's some where you can have labels, and these don't look interesting here, so I'm going to show these live, because really what these are is you can click on these and drag them around. Again, we have the our Gaussian texture map or transform editor that we saw earlier, and this one actually has a plus, so I can add multiple texture maps, and so I can look at this rib cage with multiple different texture maps multiple different transfer functions added together. And then there's this box one where you can move the shape. So anywhere where there's a green ball, I can move it, change things around. This one over here with the 2 dots is, you may not expect to be, this is the line widget. And so why is it the line widget? Well, because the line has two ends and you can move the two ends around. So these are basically the parts you grab and you can move that around. So let's go back and take a look at that and the what was the one 2 times ago? Oh yeah, the volume cube. We'll take a look at the volume, ISO volume real quick. All right. So I'm just going to go back to the main list. Oops, not mean to do that. See the ISO volume one on there? Yeah. Except I'm not too keen. Sometimes, oh, it says 0. All right, I don't know how I found the ISO volume renderer then. Here's this one. No, the volume mapper is volume rendering. The ISO is just generating a geometry out of it. So I guess I have the link on the thing so we can find it. Anyway, here's the widget for our volume rendering. You see it's actually stepping through. I can click through and do different color maps, but for the purposes of this example, it continuously changes the thing. And so I can move this around. So I've got it as a square right now. And somehow we can make it more opaque and less opaque. Right, so I have two maps going on right now, right? So I have this one and this one. So if I make this one less and less opaque, we can see through. This one's kind of the skin, right? And this one, I can change the shape through this box here. I can slide it by grabbing kind of just anywhere else in the data, and I can shrink or expand the width of the Gaussian by clicking on the bottom thing. So it's actually far more improved interface than what we have with the other volume visualizer, the VR volume visualizer. All right, so there's that one. Let me just go, I think I can probably just type in here ISO volume. Nope. All right, well, we won't worry about that. What was the other? Oh yes, let's go to the widgets. Even though we're not going to look at the code for them, I still want to show the widgets. So, oh yeah, I didn't point this out on the thing. You see here, there's example widgets box. Let's do that real quick. For some reason, they have most of the widgets under one category, and then the box under a different category. So here I can grab any of these control handles. So really, this is just kind of the code shows how to make it so you can grab handles that are in 3D, but you can grab them in a 2D interface window. We can make them unpickable, in which case I can't grab them anymore. I can turn off the handles or turn off the geometry. I can turn off the handles, just the handles. All right, and I can also remove. Oops. Anyway, so there's the box. The other one I wanted to show, well, I showed the transform editor. It might be. Tell me where it's at. Yeah, this is it. So a very simple one where we just take the ISO value. And so one of the things I meant to show too, so here it's turning it into geometry rather than a volume rendering. But down here on all the examples, it has the full code, actually most of the code. It does not have the controller.html part, which you can, get the source for by just downloading the example the old-fashioned way, using wget or something. But anyway, so here's the code. And so it has, this is the whole thing for this example, right? Except for what's stored in controller.html and except for importing the full VTK.js source code, or at least the parts you need. So all the examples, by the way, have this source code down there. I didn't scroll down for all of them to see that though. All right, I just want to show a couple more examples and then kind of wrap up. Or discuss a couple more examples, I should say. So there's a tube, whoops, wrong way. A tube filter, so if you have line data, which can be very thin, you can put that through a tube. But in addition to just making it thick, you can also, as you see in the controls here, so this is not an interactive picture, but there's a button here that says, a chooser here that says vary radius off. I can turn this to different options, one of which is set the radius based on this, a certain scalar value. So here it's a constant radius, but I could make it so it's thinner down here where the values are lower and then gets thicker up here. I'll just leave that as an exercise for later. Here's the code for doing that. So there's a tube filter, which takes as an input some poly data, which are lines, and then it takes the scalars array, and that's point data, and it's also called scalars. So it's a scalars named scalars, which is not really a great way to name your examples. Anyway, so you set that tube filter to that input, and then I'm not showing the mapping. Then you send it through the polygon mapping, and then you get, and the rendering, you get this, right? So, and here's number of sides, which I can change, number of sides, but by default, it sets it to 50, and there's some other controls there. So here's the glyph mapper that they give an example for. So in this case, they have some faux data that they pretend the temperature is, I guess, larger at the top, although it has a flow. So maybe this is some sort of temperature colored by temperature, and there's some sort of flow in the room. Anyway, it's just mathematically generated data. And then you can choose the resolution of your data set here. So there's just a plane of data that they map a glyph to. Here's the code here, which is really, really this, basically the same as what I already showed. But anyway, so there's their example of the glyph. There's a streamline, which we didn't talk too much about vector data. So here you can take vector data and show how a particle, if it was released at this one of these white squares, how it would flow through this box here. It's pretty simple flow in this case. But how each particle would flow. You can change the resolution of the volume. Of course, it's this is for a single time step, which means once the particle's released, it's basically, it's going on a same trajectory as if the flow wasn't changing, or another way to put that is the particles are moving infinitely fast. So again, it's faux data that's calculated within the script. So if we go click on that page, and we scroll down, we'll see where that's like faux data is generated. This also has the streamline class has multiple inputs. So you have to have the input of the flow data and the input of the sources. So the plane sources is where all these white cubes are, right? So anywhere there's a point on this plane, that's where a new particle is going to be released from. And then we generate an outline filter to follow the path of any particle. And then we could put a tube on that to make them thick, right? Make them stand out a little bit better. So that's kind of just how VTK typically works, right? You say, oh, I have this data I want to do a flow of. So first you have to have your vector source data. You have to have some place where particles start from. You put those both into your streamline thing. Then to actually see it, you have to tell it, oh, turn that path into a line, and then later turn that line into a tube to make it a little bit easier to see. And the kind of the next two more examples I want to talk about, and then we'll wrap up. This one's pretty interesting. So VTK has a calculator filter, which lets you basically do any arbitrary formula. And so they have their example, which I'll run this one live. Again, it lets you set the resolution of this plane. We can warp it. So here's where they do some warping. So here, the higher values are red, and so those get warped up higher, and whoops, and the lower values are blue, so they don't get warped as far. But here, the coloring, and thus both the coloring and the warping come from the same data, which is this formula here. The X value shifted over half, so this is right. So values are from 0 to 1, so they're shifting it to be from -0.5 to +0.5, and they're squaring it, and then they're squaring the Y value, and then they also square, well, the Z value is 0 to start with, so that doesn't do anything. But anyway, so we get this circular pattern by doing that. And here's the kind of interesting thing. So there's a function then, or a class called VTK calculator, which when you get an instance of that, you can create a formula. And so there's a few arguments to the formula. One is, what are you going to apply the formula on? And so I didn't mention it today, but I've mentioned it in the past. We have a VTK data set has a cell, right? If it's a 3D volume, there's a little cube, which is the cell. We can have a data that's the data of that whole cell or the center of that cell. We can have data that's on any of the corners of that cell, which are the points. And then you can also have other data that's associated just kind of generally with the cell, which is called field. But everything actually is a subclass of field. So the points are then the corners of this two-dimensional data set, and the cell would be the center of that data set. So we're going to apply our formula to the points. Right, so you could have input data if you wanted that you want to apply, but we don't need it. We're just, in this case, they're just taking the location and turning it into a number. And then the output value will be called Z, which we don't actually see here because it's gonna be the first scalar in the list, and so it gets colored by the first scalar. Down here then is something that was new to me, this equal arrow thing, which is I guess a JavaScript / ES6 thing or something, some sort of web standard. Right. So yeah, in my mind, thinking to my old computer science days, I think it's kind of like a lambda function, right? Where it just encapsulates a function. You tell it what the arguments are. So here the argument is X gets applied to this thing, and then whatever the result is gets put into what our variable name is up here. So here I could put this, if I called this Z everywhere, then it'd get mapped back to Z, and that'd be a little confusing, I guess. But anyway, so we're just squaring the X value, squaring the Y value, and then adding a little bit so that it floats above the plane. So yes, good question. So X is the point, the location of the point. It's a vector. So X sub 0 is the X value. X sub 1 is the Y value, right? And then if there was X sub 2, that'd be the Z value. So yes, good question, thank you. Right, right. I probably should have chosen a different name. Well, this is actually their code, but I should have renamed it for my slide, other than to be consistent with their thing. Anyway, so this is also, you notice this is called simple, set formula simple. They also have a just set formula, which has basically the same 3 arguments, but a lot more expanded upon. So you can actually do longer, you can do loops and stuff like that. You can tell it a lot more information about the data that's coming in and the data that's going out. And so I'll run that in a minute. But before I do, I'll talk about the other feature, and that is that I have built-in virtual reality, which I have not tested yet because it doesn't work on a Mac. You have to have a VR-ready machine for it to work. But that render that we talked about, so remember we had that full screen renderer. So you can get the OpenGL render window, so actually link to the underlying graphics hardware, and then just say start VR, and it'll go into VR mode. Have you tried this?
When I just now pulled up one of the examples,
yeah.
It launched VR.
Oh, did it? Okay. Right, right. Yeah. And then you can, in this case, if you hit the E key, you can toggle between VR and not VR. So it'll turn VR off and go back to standard monoscopic view on your desktop. So anyway, so it's VR ready, which is pretty cool. And pretty simple function calls to enable and disable VR. So I won't be showing you that one, but let's go take a look at that calculator one real quick, and then we'll call it a day. There we go. All right, so here's the calculator. So the picture, when I took my picture, I rotated it a little bit. Again, I can change the resolution of the underlying data set, right? And you can see when we make it coarser that our data gets pretty coarse. So there's a warp function happening here. If I scroll down here into the code, there's a warp in here somewhere. Now, let me scroll up. In order to highlight that, this displacement scale, oh yeah, so this is a factor that gets applied to warp, so I can multiply the normal warping value by some scale. If I multiply by 0, it just goes back to where it was. I can turn off that plane on the bottom. Oops. I don't know what that's doing though. That's weird. Oh, I'm clicking on the wrong thing. Turn off the plane on the bottom, and there's actually 2 formulas, so let me increase the resolution. So there's a choice of default formulas which are changed if I click on these 3 dots. So one is this cosine sine pattern, kind of a wavy sort of pattern, and the other was just that circular pattern. But I can also actually type in my own formulas here, which I hadn't really thought of any good ones to type in yet. So I'll do something super simple, and we'll just make it 0.5, right? So there it is there. I could do, I guess, x sub 0 times 2 or something. So let's see, is that warping? Oh, did I misformat? I have to bring it, oh. Oops. There we go. All right, so now you can see it just makes this ramp, right? And I can control the steepness of the ramp. All right, so there's a simple one. Anyway, have a formula when we try. We can just do, oops. Oh, what'd I do? I don't know what I did. Start over. I think we probably just take, no. I'm trying to type cosine. But as soon as I hit C, that disappears. Oh. Oh. So that's a user interface issue right there, I think. Yeah, I can't type the letter C. Well, I guess I could take, maybe I could type sine then. Let's try sine. Of course, so I think this x does go 0 to 1, so I think we'll be safe there. Oh. Well, that's not very interesting.
Yeah, I'm curious. Since this is JavaScript, you might have to say math.sine.
Oh, okay.
It's curving.
Yeah, it is curving a little bit, yeah. Actually, their other formula has some cosines and sines in it, so I guess there you go, yep. All right, and so that was the last example I want to show. I think this is kind of one of the cooler ones that you can just kind of put these formulas on there arbitrarily, and it's kind of, ParaView lets you make the same sort of in-tool calculations. And I'll just put up my final slide just for the video editors. Oops, wrong way. There we go. All right, any questions that we haven't addressed while we were going? Yes, Dave.
So just learned how to do this visualization stuff.
My microphone wasn't on. You did? I did. All right, maybe it's picking up off my actual Mac then.
Okay.
Well, that would be good because I didn't record the audio on Dave's somehow either. Yeah.
You're into visualization, not.
That's right. That's right. That's right.
So my question is, we've now learned how to do visualization on the web. Why would I want to do that, and what kind of limitations does that platform have?
Right. I guess why you want to do it is easy delivery to customers, right? So you can be modifying or fixing bugs, and it just goes straight to their web page. Of course, if you're a customer, sometimes that's a problem if they got workarounds, right? And now you've kind of undermined their workarounds to things. But I think quick deployment is a good way for doing that. Good use for that. What was the other part of your question?
I guess why wouldn't I want
Right.
to deploy it on the web?
Right. For that, I don't know, unless you have like big data sets, right? If you're dealing with super huge data sets, you don't have to either upload the data, like with their tools, upload it to their thing and then have it regurgitated back to you in geometric form. Or if the calculations are happening in the client side, right? And you have a lot of data. That means that if somebody's visualizing it, the client side has to upload that stuff to the web, right? Yeah. Right. We saw that. We had to wait for data a couple times for some of those examples, and those were like 30 megabyte files or something like that. Well, maybe one was larger than that. Maybe a couple gigabytes for one of those. Yeah. But yeah, in my mind, it's pretty cool, other than I'm not a huge fan, I guess, of JavaScript. But yeah. I guess, yeah, it's mostly just not knowing all the ins and outs of it. All right, any other questions? All right, well, hopefully audio worked. Or... You can still hear me? All right, so it must be coming through my laptop rather than through the thing. It's good that I've been speaking kind of loud, I guess. All right, very good. Well, so make sure you come next week for Dave, so that he's not talking to just Essen and I. And I'll do more recruiting too. All right, very good. See you guys later.